So in this video, we're going to talk about energy conservation. So we've talked about work, we've talked about power, we've talked about the types of energy, and so now we're going to talk about energy conservation. So the biggest thing about energy conservation is exactly what it sounds like. Energy is conserved. So we've been talking about kinetic energy and potential energy. And so when we talk about conservation of energy, at least in this unit, we are talking about how the total amount of energy, so total mechanical energy, which means the total energy of motion, total mechanical energy, will always stay the same. At the top of the hill, we have all potential energy. At the bottom of the hill, we have all kinetic energy. And as the object is going down the ramp, potential is converting to kinetic. So even though we think about total potential, like the maximum amount of potential energy an object can have would be at the top of the hill when it's not moving, because an object is moving does not mean that it has no potential energy. An object can be moving and have potential. In this example, it has the maximum potential at the top when it's not moving, but the potential transfers to kinetic. So potential decreases as it goes down the hill, kinetic increases as it goes down the hill. But no matter what, if you were to take kinetic and potential and add them together, you would get the exact same amount at every single time. Best example of conservation of energy is a roller coaster. If you think about how a roller coaster works, over here we have the chains with the initial ramp. So the car is pulled up this ramp by the chains, where it goes click, 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 all the way to the top. What it's doing is the chains are doing work on the train of the roller coaster. Whenever work is done, the object is gaining potential energy. So as it goes up the hill, it's gaining more and more potential energy from the work done by the chains until it reaches the top. And what you should notice is that roller coasters will never have a ramp or a hill taller than that initial spot. We'll talk about why in just a second. But whenever it reaches this point, it has its maximum potential energy. As it's going around, notice how it's going in a downward direction very slightly. That potential is being transferred to kinetic just a little bit until we reach right here. With these great big drops, you have all of that potential at the top of the hill being transferred to kinetic at the bottom. That's why the trains are slower at the top than they are at the bottom of the hill. Even when you get to this secondary hill, you're going slower up here than you are down here. And that's because your kinetic at the bottom here is now being transferred back into potential. So lots of potential being transferred to kinetic, lots of kinetic being transferred back to potential, lots of potential transferred back to kinetic, lots of kinetic. So it's potential, kinetic, and by having all of this transfer of energy, that's why the ride is so fun, that constant change in speed with the up and down motion. So the idea of conservation of energy is that energy cannot be created or destroyed. So it cannot be created or destroyed. It's simply transferred. So here, the total energy in the system, which is that total mechanical energy here, so see we've got our little pillars here again, just like before, is going to be equal to the potential energy plus the kinetic energy at any given time. So at the very top of the hill, let's see if I can restart this. At the very top, it's all potential. As it goes down the hill, potential becomes kinetic. The bottom, it's all kinetic. And as you can see, as it's going through these loops, the kinetic becomes potential, becomes kinetic, becomes potential, kinetic, and so it just keeps going and transferring back and forth. So as you increase the height again, your potential will be going back up because kinetic is becoming potential. And then as it comes back down, that potential goes back to kinetic. But at any given point along the ride, the total mechanical energy remains the same. So pendulums work the same way. This is why if you have a pendulum style clock, it will never stop. So at the top of the swing, it's all potential. At the bottom of the swing, it's all kinetic. Then it goes back up, all potential. And so this potential transfers to kinetic. There we go. So the potential transfers to kinetic, then the kinetic transfers back to potential. And it just keeps going back and forth and back and forth. So, in reality, does a roller coaster's final kinetic energy equal the initial potential? And it's no, it doesn't. The reason why is because not all of the potential energy is transferred to kinetic. Some of it is transferred to friction, wind resistance, and heat. If the roller coaster were absolutely frictionless on the moon, maybe it would be. But the idea is it's not destroyed. Okay, so energy is still not destroyed, it's just simply lost as other forms of energy. So friction creates heat, and that heat is a type of energy. It's a transfer of energy, movement of energy. Wind resistance is a type of friction, which also creates that heat. So even though the energy is still conserved, some of it is lost. That's the reason why roller coasters are built where the tallest hill is always the first one. Because as it's going down, going back to our picture, as it's coming down this hill, those wheels and the cars in contact with the track have friction, losing some of that energy as heat. Plus, the wind resistance of the car and the people is also producing a type of friction, which is losing some energy as heat. That's why the tallest hills are at the beginning and the smallest hills are at the end. So let's do an example, one of these roller coaster examples, using our equations for potential kinetic energy and also looking at this conservation of energy. Now, the biggest thing about this introductory class is that we have to assume no loss of energy. Okay, so assume no loss of energy. We're assuming that this is a frictionless roller coaster with no air resistance as well. So the tallest wooden roller coaster has a height of 60 meters. So height is 60 meters. If one of the trains has a mass of 1230, oh, that should be kilograms. So 1200 or 1230 kilograms, which is mass, when loaded, how much potential energy does it possess at the top of the ride? So in other words, how much work does those chains do the chains do whenever it pulls it up to the top of this hill? So potential energy is mgh. So our mass is 1230. G is always 9.8. And our height is 60 meters. So if we do 1230 times 9.8 times 60 in the calculator, we get 723,240 joules of potential energy. That is a lot. But that's because this is a full loaded train. So think about how many cars might be in a train and all of the people sitting on it as well. So huge number. How much potential and kinetic energy would it possess halfway down the hill? So we said that at the top of the hill, it's all potential energy, and the kinetic energy is 0. At the bottom of the hill, it's all kinetic energy, and the potential energy is now 0. So what do you think happens right here at this halfway point? Well, potential will be half of the original, and kinetic energy will now be half of its max it will become. So if at the top, the potential energy, so at the top, is 723,240 joules, then the potential energy halfway down will be half of this original, which will be 361,620 joules. And the kinetic energy will be the other half of this original. So the potential, remember the total energy, so total energy is equal to potential plus kinetic. So if half of the total energy is potential, then the other half has to be kinetic. So kinetic energy will also equal 361,620 joules. So what will be the kinetic energy at the bottom of the right? Well, we just talked about it here. It will be all kinetic, no potential. So kinetic will be the original, 723,240 joules. And the last question would be, what would be the speed at the bottom? So again, this is all assuming there is no loss to friction, air resistance, or heat. So we would need to use our kinetic energy equation. KE equals 1/2 mv squared. Our kinetic energy is 723,240. That's equal to 1/2 of the mass. Mass of our roller coaster was 1230. So 1,230 kilograms times v squared. So 723,240 equals half of this, which is 615 v squared. So then we divide by 615, and we're left with v squared equals 1176. Then to find v, we'll take the square root. And so our v is 34.3 meters per second. So pretty fast. Lots of fun.